Welcome to the deep dive. Ever feel like you're just swimming in data, especially in fields like, say, design or architecture? It can get really complex really fast.
Oh, absolutely. Information overload is a real challenge.
So today, we're going to tackle that. We're diving into object-oriented programming, OOP, and data structures.
Think of them as ways to bring some serious order to all that chaos, tools for clarity and control.
Exactly. And our mission here is to pull out the really key ideas, the practical stuff from a recent workshop. We've got the recording, the documents, English and Korean versions.
Right, we're sifting through it all to find those essential nuggets for anyone wanting to get up to speed quickly. It's about managing information efficiently, maybe even elegantly.
Making complex tasks feel, well, less complex.
Precisely. Understanding those core principles gives you a real edge.
Okay, so let's start unpacking. When you first deal with data, it's often just individual variables, right? Maybe you group them into arrays or lists.
Yeah, those are the basics. But the workshop really highlighted dictionaries.
What's the big advantage there? Why are they such a step up from, say, a simple list?
Well, it's about adding meaning. A list is just a sequence. Item 0, item 1, item 2. Maybe item 2 is a window width, but you have to remember that.
Right, you're relying on the position.
Exactly. With a dictionary, you use a key, like the word width, and you assign the value to that key. So instead of my list 2, you have window width.
Ah, okay. So it's self-explanatory, much clearer.
Instantly clear. It makes your data easier to understand, less error-prone, especially as things get bigger. How do you usually handle your info? Ever wish you could just label things directly?
Definitely. I can see how that avoids a lot of confusion. So dictionaries are one step. What comes next?
Well, dictionaries help organize the data itself, but then you have actions, functions that use that data.
Right. And the workshop made this point, since we have a data, the function should be there. Why is that pairing so important?
It's about organization and, honestly, sanity. If your data, like shape dimensions, is over here, and the functions to calculate area or perimeter are way over there,
Things get messy. Hard to track what depends on what.
especially in big projects, yeah. So OOP suggests bundling them. Put the data and the functions that operate on that specific data together in one package. That package is a class.
A class. Okay. The workshop called it a blueprint or a template.
Exactly. It's the plan. It doesn't do anything on its own. It just defines the structure and the capabilities.
And then the object is the actual thing made from the blueprint. The workshop said object is the instance from the class.
Perfect. Think of a cookie cutter. That's the class. It defines the shape.
Okay.
Each cookie you actually cut out, that's an object, an instance.
Mm-hmm.
Or a car class defines what a car is. Color, doors, engine, maybe methods like start or accelerate.
So my specific red sedan is an object, an instance of the car class.
Precisely. It has its own specific values,
Hmm.
red color, V6 engine,
Oh.
but follows the blueprint defined by the class.
That cookie cutter analogy really helps. Okay, so we have classes and objects. Then the workshop got into some powerful OOP concepts like inheritance. They used a polygon inheriting from a polyline. Why do that?
Ah, inheritance. This is all about efficiency and reuse.
Right.
Why reinvent the wheel, right?
Makes sense.
So a polygon is basically a special kind of polyline. It's a sequence of points, just like a polyline, but the last point connects back to the first, closing the shape.
Okay, so they share a lot of the same basic data structure.
Exactly. So the polygon class can inherit all that point handling stuff from the polyline class. The workshop quote was great here. Polygon is identical as polyline, so that's why we basically inherit all parameters from polyline. Makes
Yeah.
sense, right? Because we already learned and we don't need to worry about except for rendering.
So you don't rewrite the code for storing points, you just add the polygon-specific stuff.
Right, like maybe how to fill it when rendering or how to calculate its area, which a simple polyline wouldn't need. It's like taking a basic recipe and just tweaking it for variations. Saves a ton of work.
That's really smart. Avoids repeating yourself. Okay, another concept was encapsulation. The example was a point class, bundling position data, and a render function. What's the benefit there?
Encapsulation is like creating a protective capsule. You put the data, the coordinates, the position, and the methods that are meant to work with that data, like render, inside the class.
And this protects the data.
Yes, it controls access. Ideally, other parts of your code shouldn't be messing directly with the internal position data. They should use the provided methods, like render. It prevents accidental changes, makes debugging easier.
Yeah.
It's like keeping the engine inside the car's hood, not just out in the open.
Got it. Keeping related things together and protecting the internals. And you mentioned rendering the workshop hinted that render might work differently for a polyline versus a polygon that touches on polymorphism.
You got it. Polymorphism meaning many forms. It's this cool idea where different objects can respond to the same message or function call in their own unique way.
So you could tell both a polyline object and a polygon object to render, and they'd just do the right thing. One draws lines, the other draws a filled shape.
Exactly. The workshop didn't go super deep into it, but that's the essence. You can treat related objects uniformly, but they still behave correctly according to their specific type. Very flexible.
Okay, this is clicking. Now, the workshop also talked about thinking in objects, modeling the real world. They used the term ontology. What's that about?
It's about abstraction, really, looking at the world and figuring out how to represent its structure in data. The quote was quite evocative. Basically, look at everything around you and think, how can I abstract this?
Turn real things into data structures.
Yes. Identify the key entities, their properties, their relationships. Like the workshop examples, a door or window belongs to a wall. A wall is part of a room.
Ah, so you build up these hierarchies. Door inside wall, wall inside room?
Precisely. You start modeling the relationships and structure of the real thing, like a building, digitally. It helps manage that complexity.
And they suggested exercises like modeling a calculator or a vending machine.
Yeah, great practice. Thinking about a calculator. What data does it need? The current display, maybe the last number entered, the operation selected. What can it do? Add, subtract, clear.
So you define a calculator class with those attributes and methods?
Exactly. It makes you really break down the components and functions of everyday things. Really helps solidify that object-oriented mindset.
Makes sense. The workshop also introduced design patterns as reusable solutions. Two came up, singleton and adapter. Let's start with singleton. What problem does that solve?
Singleton is for when you absolutely positively need only one instance of a class in your whole system. The workshop was emphatic.
Only one. Just one.
Okay, like what? Why would you need only one?
Think about something like global application settings, or maybe a single connection pool to a database. You don't want multiple independent settings managers potentially overwriting each other, right?
Right, that could cause chaos. You need a single source of truth. Exactly. The singleton pattern ensures only one instance gets created and gives everyone a single, controlled way to access it. It's about control and preventing conflicts with critical resources.
Got it. One instance only. And the adapter pattern. They use the analogy of a power adapter. Okay.
Yeah, that's a great analogy. The adapter pattern is like a translator or, well, an adapter. Imagine you have two systems, maybe some new code and some older code, and they don't quite match up. Their interfaces are different.
They expect different inputs or provide outputs differently.
Right. And the workshop quote mentioned this. Modifying the old code directly can break everything that depends on it.
So you don't want to rewrite the old system.
Preferably not. So you create an adapter. It sits between the two systems, translating requests from one format to another, allowing them to communicate without either needing to change internally.
Like the power adapter lets your European plug work in a US socket. It bridges the gap.
Precisely. It helps integrate components that weren't originally designed to work together. Very useful.
Okay, bring this back to design tools. They mentioned Grasshopper, the visual programming environment, and data persistence issues. How does OOP help there?
Ah, yes, a classic Grasshopper challenge.
Yeah.
Often, data calculated inside a component disappears once it finishes running, right? It doesn't persist.
Yeah, it resets on the next run unless you wire it out.
Right, but OOP offers a solution, as the workshop pointed out. Joey, boy. Yes, yeah. Yeah, Joey. Classes make persistent data possible. You can store data as attributes within an object. That object can be kept in memory, perhaps using Python script context or similar techniques in C#, even after the component finishes its calculation. The object persists, and so does its data.
Okay, so the object lives on between runs, holding the data.
Exactly. It lets you maintain state, build up information iteratively, which is crucial for more complex design workflows in Grasshopper.
So you could even build your own custom Grasshopper components using classes, like the mirror polygon example they maybe mentioned, encapsulating the data and the logic together.
Absolutely. That's the power move. You start creating your own high-level, reusable design tools within Grasshopper, making your definitions much cleaner and more capable.
Very cool. Finally, the workshop really pushed for practice, right? Reviewing code, thinking about games like Street Fighter.
Definitely. Active learning is key. Look at the provided Python JS code, explore sites like W3 Schools, try modeling things yourself. Think about Street Fighter characters, what are their attributes, health, special moves, what are their methods, punch, kick, fireball.
Huh, okay. Applying it everywhere.
Yeah, revisit old projects with this OOP lens. Build that knowledge tree they mentioned. It's about making these concepts your own through application.
It really feels like it all circles back to organizing information, doesn't it? OOP and good data structures give you a framework to handle complexity, whether you're coding or designing.
It's a powerful mental model, a way to structure your thinking and your code, making things clearer, more efficient, more controlled.
So for everyone listening, here's a final thought. Pick something familiar from your day. Your commute, making breakfast, anything. How would you model that using objects? What are its parts? What does it do?
Thinking that way, applying these OOP ideas, can really open up new perspectives on problem solving.
Absolutely. Check out those resources, try the exercises. It's definitely a journey worth taking. Thanks for diving deep with us today.
My pleasure. It's fascinating stuff.